For as long as there has been life on Earth, the sun has been our eternal companion. It is the silent fire in the sky, a cosmic heart that has burned without pause for more than 4.5 billion years. Its light has shaped oceans, carved mountains, and guided the rise of civilizations. Every heartbeat of time we have ever known is measured by its steady glow. But this blazing constant, this guardian star, is not as constant as it seems. Deep within its fiery core, forces beyond imagination churn and twist. Its heartbeat is shifting. Its rhythm is changing. Even now, as you hear these words, the sun is undergoing a transformation we can measure and feel. Imagine a lantern at the top of a watchtower beginning to flicker. Imagine a furnace whispering secrets of its own inevitable future. The sun, the very engine of life, is speaking, not in words, but in solar storms, in magnetic pulses, in waves of radiation that ripple through space. To understand these changes is to glimpse the story of our planet's fate. The sun is not merely shining, it is evolving. And as it evolves, so does the destiny of everything that lives beneath its light. If you are new here, join the journey. Like, subscribe, and let's begin. Long before telescopes and probes, when Earth was young and sky watchers stood beneath the glowing dome, the sun was already speaking in silence. Ancient Chinese records, compiled in the Book of Changes, speak of dark blemishes crossing the solar disk, spots so large they could be seen with the naked eye, tracing slow arcs across the bright face of the star. These were not myths of gods or portents, but observations, the earliest footprints of the sun's changing heart. Scholars today believe these records date back to around 800 BCE. In Babylonia, astronomers kept diaries of the heavens. The astronomical diaries from Babylonia contain entries between 652 BCE and 61 BCE that describe aurora-like phenomena, glowing curtains in sky, unaccounted flashes of color. These anomalous lights hinted not at spirits, but at solar storms reaching across space. Then centuries passed and instruments sharpened. By the Renaissance, when Galileo turned his telescope to that blazing orb, the sun's purity was shattered. Galileo's drawings revealed sunspots, dark, shifting, imperfect. The sun, so often represented as perfect and constant, revealed itself to be blemished, changing. The image startled the learned world. Imperfections, movement, signs of something deeper. In the centuries that followed, interest grew. In the 19th century, a German astronomer named Samuel Heinrich Schwabe devoted himself to sunspot counts. Over many years, Schwabe noticed that the number of sunspots rose and fell in a regular rhythm, about every 11 years. This rhythm came to be known as the solar cycle. Scholars realized the sun was not steady, but pulsing, with magnetic moods, carrying consequences for Earth's skies and magnetic field. Solar flares and coronal mass ejections entered the record next. In 1859, the Carrington event was observed. An enormous solar flare paired with a coronal mass ejection so powerful that telegraph systems sparked and auroras shimmered near the equator. It was perhaps the first vivid demonstration that the sun's outbursts could reach Earth and disrupt the world. With the advent of more sophisticated tools in the 20th century, the sun's secrets came into sharper focus. Observatories in space, SOHO, Solar and Heliospheric Observatory, launched in 1995, SDO, Solar Dynamics Observatory, launched in 2010, began to monitor solar activity day and night, in unseen ultraviolet wavelengths, in X-rays, mapping magnetic fields, tracking plasma flows. These instruments revealed sunspots emerging, growing, twisting, decaying. They saw coronae boiling, loops of magnetism rising. They watched coronal mass ejections hurl billions of tons of solar plasma into space. Over recent decades, a persistent picture emerged. The solar cycle, once regular, is showing signs of strange behavior. Cycle 25, the current cycle, already demonstrates flares of unusual intensity, with strong bursts recorded by SDO. The sunspot number is rising, polarized magnetic fields shifting, coronal mass ejections arriving more frequently and with greater energy. Satellite data show that active regions on the surface of the sun are more complex, more twisted, storing free magnetic energy that can power explosive events. Scientists compiling records from Chinese chronicles, ice cores, tree rings, and modern observations find anomalies, periods when solar activity dropped, as in the Maunder minimum, or rose unexpectedly. These patterns suggest that the sun's magnetic engine, its internal dynamo, is not always stable. It pulses, sometimes uncertain, sometimes alarming. At this present moment, instruments observe a sun that seems to be accelerating. Sunspot counts are increasing more steeply than some models predicted. Solar flares are reaching higher energy classes more often. Coronal mass ejections appear more violent, their speeds higher, their magnetic fields more disturbed. Real-time monitoring by NOAA, NASA, ESA reveal storm warnings, radio blackouts, geomagnetic impact potentials rising. The lives of satellites, astronauts, power grids, communication systems all teeter under the growing weight of solar temper. This discovery phase is more than historical reconstruction. It is the unveiling of a sun alive with change. From ancient naked-eye observers to modern detectors in space, the evidence accumulates. The sun is not a static star, but a dynamic, unpredictable force. It pulses in cycles, it erupts, it convulses, and now it seems to be speeding up. The first hints of this transformation came long ago. The full story is still unfolding. For countless centuries, the sun was held in the human imagination as perfect, unchanging, a fixed orb in the heavens. Philosophers spoke of its immaculate light, poets of its eternal brilliance. Astronomy, until fairly recently, treated that light as unalterable. Stars were steadfast. The sun especially was the measure of constancy. Yet the first tremors of a different truth were gathering. Albert Einstein, in 1917, enshrined among his field equations a model of the universe as static, unchanging, balanced, infinite in its quietude. Science looked outward and imagined space itself unmoving, time merely a canvas upon which events occurred, but not a stream that shifted or strained. Einstein introduced the cosmological constant, L, precisely so that gravity's pull would not collapse the universe inward. For a time this seemed elegant, even inevitable. Then observation crept in. Hubble's redshifts, Lemaitre's expanding cosmos. Little by little the steady tableau cracked. Einstein himself would eventually abandon his static model, recognizing that the universe, like the sun, was not immune to change. The idea that celestial bodies might vary, that their behavior could amplify, ripple across space and time, came to seem not heretical but fundamental. In parallel, the Earth itself bore witness to one of the most jolting revelations of solar power, the Carrington event of 1859. On September 1st, Richard Carrington, an amateur astronomer gazing through his telescope, saw a sudden flash, a white light flare arching across sunspots. For the first time, someone saw a solar flare with their own eyes. Roughly 18 hours later, the solar eruption caught up with Earth in a tempest of magnetic disturbance. Telegraph wires sparked. Operators reported shocks. Auroras, vivid and raging, lit skies near the equator. The shock was not just that the sun could erupt, but that its eruptions could touch human life, that a star nearly 150 million kilometers away could reach across space and unravel technological threads, ignite wires, confuse compasses. The sun ceased to be simply a distant furnace. It became an actor in Earth's fate. Soon after, scientists found that the sun followed rhythms, cycles of magnetic dance. In the early 19th century, Samuel Heinrich Schwabe charted sunspots and discovered that every roughly 11 years, the number of spots would rise and fall. A solar cycle. The sun's magnetism, its twisted surface, its flaring, had a beat. Decades later, observation of magnetic field reversals, polarity flips, would add mystery. The sun's magnetic north and south poles switch approximately every 11 years within a broader cycle. With each flip, magnetic energy is stored and released in ways scientists are still decoding. Such flips intensify solar storms, drive coronal mass ejections, and make the solar wind more turbulent. The idea that the sun is a living star, evolving, tempestuous, stood in stark contrast to the earlier image of perfect celestial constancy. This idea unsettled centuries of thought. Scientifically, it raised paradoxes. How does the sun sustain its fusion, its magnetic dynamo, its cycles for billions of years? What controls the variations, the highs and lows, the sudden bursts? Moreover, these changes challenge assumptions. If the sun's behavior shifts, then Earth is no longer safe from the cosmic weather beyond its atmosphere. Climate, technology, life itself become vulnerable. The margin for error shrinks. The recognition of solar cycles and magnetic flips rewrote the story of the sun. No longer was it the unchanging centerpiece of the sky. Its variability meant that stars are dynamic, that even what seems eternal is subject to forces unseen. Thus, the scientific shock took root. A star, held sacred in human thought, proved mutable. The sun, long adored as constant, was now known to pulse, to erupt, to alter its relationship with the planets it warms. Understanding these unexpected truths became essential, not merely for astronomers, but for every life planted beneath its light. The sun's changes are no longer whispers from distant pasts. Modern science listens to its inner voice through instruments that perceive rhythms invisible to human senses. Helioseismology reveals what lies beneath the glowing surface, neutrino. Detectors trace the furtive fusion reactions within the core. Together, they map the heartbeat of a star long thought immutable. Helioseismology measures oscillations on the sun's surface, waves that travel through its interior, refracting and reflecting, carrying information about temperature, density, and motion. These waves rise and fall like sound inside water, like tremors in a grand cathedral built of plasma. From those waves, scientists deduce that the sun's interior is not uniform. The tachocline, that thin shearing layer between the radiative, interior and the convective outer shell, stores magnetic energy. The interior rotates at different rates at different latitudes. Flows of plasma swirl, sink, rise. Crucially, helioseismic studies of the minimum between solar cycles 23 and 24 found that oscillation frequencies dropped, implying that the sun's near-surface magnetic field was weaker during that minimum than in previous ones. Such variation betrays deeper magnetic changes within the star. Helioseismic perspective on the depth between cycles 23 to 24. Neutrino detectors offer a second, more secret channel. Neutrinos escape from the core of the sun almost unhindered. Their flux tells of fusion happening in real time. The solar neutrino problem, the long discrepancy between predicted neutrino numbers and observed ones, once troubled scientists. It was resolved by understanding that neutrinos oscillate, change flavor on their way to Earth. But the data gathered since validates that fusion remains constant on long timescales, even as magnetic and surface phenomena vary. Fusion reactions power the sun's inner furnace. Changes in how that power expresses outward create the observed variability without altering the fundamental source of light and heat. Observatories monitor the visible surface, ultraviolet corona, magnetic fields, solar wind, and sunspots. Instruments such as the Solar Dynamics Observatory, SDO, capture images in many wavelengths. Magnetographs measure field strength, mapping, lines of force that writhe around sunspots and active regions. Solar wind monitors record streams of charged particles reaching Earth's magnetic shield, revealing how the sun pulses outward. Sunspot counts serve as a rough barometer. More sunspots usually mean more magnetic complexity, more flares, more storms. Patterns emerge across decades and centuries. The solar cycle, the index of activity rising to a peak and falling again, roughly every 11 years, remains the basic beat of solar change. Above that, longer cycles appear. The Hale cycle of about 22 years, when magnetic polarity flips. The Gleisberg cycle, approximately 8,100 years of modulation in strength and amplitude. But anomalies have crept in. The Maunder minimum, 1645-1715, remains a stark example. Very few sunspots, low magnetic activity, coinciding with colder climates in parts of the northern hemisphere. Yet even during that near blanket of quiet ice core, and nitrate proxy records show periodicities. 11-year and 22-year cycles persisted, faint echoes of solar dynamos still pulsing in subtle fashion. Even during times of near silence, the sun did not wholly rest. Dome Fuji ice core nitrate concentrations. Another anomaly, the recent minimum between cycles 23 and 24 was unusually deep. Helioseismic data revealed that during that period, global oscillation frequencies were significantly lower. The magnetic field near the surface was weaker. The quiet between cycles was longer, darker. Then, instead of returning to previous expectations, the next cycle, cycle 25, began showing surprisingly stronger sunspot numbers and flare activity, exceeding some earlier forecasts. This suggests not a simple return to baseline, but perhaps a subtle reconfiguration of solar magnetic behavior. Scientists compare proxy records, ice cores, cosmogenic isotopes such as carbon-14 and beryllium-10, tree rings, aurora chronologies, with modern observations. Ice cores from Antarctica, like the Dome Fuji station, contain nitrate signatures that record solar cycles even centuries ago. Tree rings show variations in cosmic ray exposure tied to solar magnetic shielding. Aurora records in East Asia, in European Chronicles, describe skies glowing in red or green, periods of aurora that correspond to solar maxima. These data allow reconstruction of solar activity well before telescopes. They reveal that grand minima are not unique, that the sun has wandered through long and short periods of change many times across millennia. In recent decades, satellite data show that solar irradiance, the total energy output at all wavelengths falling on Earth, varies only slightly across cycles in visible light, but ultraviolet and extreme ultraviolet bands vary more strongly. Those higher energy photons influence the Earth's upper atmosphere, its ozone chemistry, ionosphere density. Magnetic storms and solar wind modulation affect cosmic ray flux reaching Earth, which in turn has effects on cloud nucleation and ionospheric currents. Emerging anomalies hint that solar cycle 25 may peak with more intensity, with more powerful coronal mass ejections and stronger flare activity than some models predicted. The rise in sunspot complexity, where sunspot groups twist, collide, produce greater magnetic shear, seems greater than in prior recent cycles. Solar wind streams from coronal holes are faster and more erratic. Magnetic field reversals show asymmetries between northern and southern hemispheres of the Sun, suggesting the dynamo generating the field may be shifting inside the star. Speculative, but credible interpretations posit that the internal dynamo mechanism, which depends on meridional flows and differential rotation, may be undergoing changes. Perhaps the flow of plasma near the Sun's poles is slowing, or convective overturn is altered by subtle shifts deeper in the core. Such changes could amplify or dampen cycles. Some models suggest that stochastic variations, random fluctuations, in the poloidal field generation or meridional circulation can trigger grand minima or unusually strong maxima. Another speculative thread contemplates whether long-term solar memory exists, whether solar activity from centuries past influences present dynamo behavior via lingering magnetic fields or structural adjustments in the plasma flows. If true, then the implications are profound. The Sun cannot simply reset each cycle, but carries history within. The deeper investigation reveals a Sun that is not merely cycling, but evolving. A star whose surface, atmosphere, and magnetic skeleton respond to forces deep inside, where fusion and plasma flows act as unseen architects. The catalogue of anomalies and patterns across time suggest that the Sun's present behavior must be read as part of a larger tapestry, one woven across centuries, possibly millennia. The Sun's mood swings are encoded in ice and wood, in auroral lights and satellite data. They tell of periods of hush and of roar. They warn that the pattern is neither strictly predictable nor comfortably gentle. In order to understand the Sun's changes now, the science must reach both into ancient pasts and into the unseen core. The deeper investigation does not resolve the mystery, it opens it further. It shows that the Sun carries within its core the power to surprise, to reshape, and to set the stage for futures not yet born. The Sun's whisper has grown into a roar. Recent months reveal its behavior accelerating far beyond expectations. What once were gentle pulses of energy now surge with magnitudes that command attention. X-class solar flares, the most powerful explosions on the solar scale, are appearing more frequently. Coronal mass ejections tear through solar space with increasing violence. Sunspot counts, once predictable, are reaching levels that challenge earlier forecasts. The star once thought to follow a rhythm seems now to improvise crescendos. In 2024, solar cycle 25 produced a sequence of X-class flares never seen in that span since reliable records began. Space Weather Live noted over 50 X-class flares during that year, an extraordinary spike. Among them, the flare of May 14, 2024, classified as X8.7, stands out as one of the strongest of this cycle. Sunspot region, NOAA 3664, became a superactive region emitting multiple intense flares in rapid succession. Observatories observed white light emissions even from solar features outside the usual sunspots, indicating that flare energy was reaching more broadly across the solar surface than is common. These are signs that the sun's magnetic complexity is growing. These flares are not mere light shows. Their power can interfere with satellite function, disrupt GPS signals, and overload radio communications. A sufficiently strong solar storm can knock out power grids, degrade spacecraft electronics, endanger astronauts beyond Earth's magnetosphere, and cause cascading failures in systems relied upon daily. As Earth's technological web becomes more fragile and interconnected, these solar eruptions pose greater risk than ever before. Meanwhile, the slow, inexorable warming of the sun is also a long-term puzzle. Nuclear fusion in the core converts hydrogen into helium, and as heavier elements accumulate, the core's pressure, density, and temperature grow. The core contracts subtly. Temperature and pressure climb. Over millions of years, this causes the sun's overall brightness and heat to increase. Long ago in its life, the sun was cooler and dimmer. Now it is hotter, brighter, and will become still more so. This process is normal in stellar evolution, but it is a slow-burning clock for Earth's habitability. Even small shifts in irradiance impact climate over geological timescales. The stakes are therefore both immediate and distant. Today's escalating solar flares may damage satellites, cut off communication, trigger geomagnetic storms. Tomorrow, the gradual brightening shifts climate patterns, alters atmospheric chemistry, tests the bounds of ecosystems adapted to a delicate balance of solar input. This tension asks a haunting question. Is the sun merely executing another ordinary cycle, a particularly strong one within known variation? Or is it entering a phase of behavior marking deeper, longer-term change in its internal dynamo? Could changes in meridional flow, convective turnover, magnetic field structure, or even core processes be nudging the star into territory beyond historical precedent? If that were true, then humanity stands at the threshold of a cosmic turning point, not merely witnessing solar peaks, but perhaps witnessing the beginning of a transformation whose full shape none can yet predict. The sun's escalating voice demands attention, not only as astronomy, but as portent. Deep within the sun's turbulent innards lies the engine that powers its restless variability. That engine is the magnetic dynamo, a process by which flows of plasma, rotation, turbulence, and magnetism conspire in ceaseless motion. Hydromagnetic dynamo theory holds that differential rotation, where the sun's equator spins faster than its poles, winds up magnetic field lines into toroidal loops. Helical convective motions twist those lines, converting toroidal field into poloidal field, which then reverses in a cycle. This dance of omega effect and alpha effect shapes the 11-year sunspot cycle, the 22-year magnetic polarity cycle, the butterfly patterns of sunspot emergence, and the periodic flips of magnetic poles. Theories of flux transport dynamo add layers. Meridional flows carry magnetic flux toward the poles, beneath the convection zone, setting timing and amplitude of cycles. Models built on these foundations predict that solar cycles can amplify or dampen depending on subtle shifts in internal flows. If meridional circulation slows, or if turbulence in the convection zone changes, the dynamo's efficiency wanes. Grand minima, periods like the Maunder minimum 2 centuries long, when sunspots nearly vanished, are among the most striking manifestations. Theories suggest that weak poloidal field and slower return flows combine to allow the sun to enter these quiet phases. On the flip side, dynamo models also allow for particularly strong cycles, when internal shear, flow speed, and magnetic feedback align favorably. Beyond cycles lie speculations drawn from observing other stars. Superflares, eruptions releasing orders of magnitude more energy than the strongest solar flares, have been recorded on sun-like stars. A recent study of over 56,000 stars similar in temperature and brightness to the sun, using Kepler photometry, identified nearly 2,900 superflares. These superflares occur on average about once per century on such stars, specifically those whose characteristics match the Sun's in many respects. The energy of some of these reaches beyond 1034 erg. Vassiliev, Uzoskin, Krivova et al. 2024. These observations suggest that mechanisms underlying solar flares and superflares may be continuous in nature. Large flares are rare, extreme cases of the same physical processes. Some speculative proposals consider whether the Sun might produce a superflare in the future. If so, extreme magnetic reconnection in very large sunspot groups, coupled with strong toroidal field, could release far greater energy than known flares. Models examine whether the Sun's present accelerating magnetic activity could increase the chance, though none conclude definitively. More provocative speculation considers whether deep, structural changes accompany or drive these variations. Could differential rotation rates, especially at the tachocline, the boundary between radiative interior and convective zone, be shifting? Could flows deep beneath the surface, or changes in how plasma transports heat outward, subtly alter the dynamo's behavior? Some global magnetohydrodynamic simulations hint that tiny shifts in convective turbulence or meridional circulation could lead to changes in cycle amplitude or even cause transitions to prolonged minima or unusually strong maxima. These theories weave a tapestry that connects the Sun's behavior not only to its own interior but to the broader story of stellar evolution. Main sequence stars, like the Sun, spend roughly 10 billion years fusing hydrogen. Over this time, their cores gradually change composition. Helium accumulates, opacity shifts, fusion builds heavier elements, and core temperature slowly increases. The magnetic dynamo depends on these internal conditions. As the Sun ages, its structure alters, even if imperceptibly with each passing decade. That evolution could influence magnetic behavior, flare frequency, or cycle strength. Astrophysicists also draw lessons from stars older or younger than the Sun, or spinning at different rates. Younger, fast-rotating solar analogues show much more intense magnetic activity and more frequent flares. Older stars, having slowed their rotation, show quieter activity. These parallels offer windows into the Sun's possible futures. Thus, theorists propose that the current accelerating behavior of the Sun might be not just another cycle, but a sign of an evolving dynamo. If flows beneath the surface are changing, if the tachocline is more volatile, if meridional circulation is shifting or weakening, the Sun may enter a phase unseen in recent centuries. All these theories remain speculative, not certain. Models differ in their predictions. Observational constraints, while growing, remain incomplete. Yet the convergence of ideas, dynamo theory, superflare statistics, stellar evolution, interior flow dynamics, suggests the possibility that humanity is watching more than solar cycles. Perhaps the Sun is stepping into a new stage of its magnetic life, a stage where variance, intensity, and risk are not just natural, but elevated. A great human endeavor now watches the Sun as never before. Instruments orbit, probes plunge, telescopes peer through shimmering atmosphere. The tools are many, each one a whisper amplifier of solar truth. The mission is no longer passive observation. It is active listening, daring, close. The Parker Solar Probe, launched in 2018, has broken records. It now skims the Sun's outer atmosphere, the corona, coming closer than any man-made object ever has. Most recently, on December 24, 2024, it passed within about 3.8 million miles, roughly 6.1 million kilometers of the solar surface, tracking waves of charged particles, magnetic fields, turbulence, and the structure of plasma under scorching heat, faster than anything humankind has launched. Its instruments endure searing temperatures and radiation to gather data about coronal heating, solar wind origins, energetic particles. The probe's findings include magnetic switchbacks, sudden reversals or kinks in the solar magnetic field carried by the solar wind, unpredicted in number and form, challenging models of solar magnetic structure. It also has observed surprisingly high energy transfer rates in solar wind turbulence deep in the inner heliosphere, far closer to the Sun than previous missions. These findings edges human knowledge into zones of mystery previously sealed. Far above Earth's thick atmosphere, the Solar Orbiter, an international mission led by ESA with NASA participation, turns its gaze to the less seen faces of the Sun, its poles. For the first time ever, the polar regions are being mapped in detail. Polar wind flows, magnetic field geometry, unseen currents across the poles. all critical to the solar dynamo, to the cycles of magnetic polarity. These regions hold clues, the sun's magnetic wellspring, where high latitude flows modulate the strength and timing of each solar cycle. On Earth, in clear mountain air or atop islands and deserts, the Daniel K. Inouye Solar Telescope, DKIST, reveals the sun's face in unprecedented clarity. Its 4-meter aperture, adaptive optics, spectral windows from visible to infrared, allow scientists to resolve structures down to tens of kilometers. Solar granulation, the boiling cellular patina on the photosphere, is seen in detail never before possible. Bright plasma rising, cool plasma sinking in dark lanes, magnetic fibrils, flux tubes threading through quiet regions, small-scale magnetic structures hitherto invisible, now measurable. The smallest scales of magnetism begin to come into view. Together, these tools compose a symphony of solar monitoring. Models of space weather prediction are evolving. Agencies around the globe simulate how solar storms propagate, how coronal mass ejections and solar flares may impact satellites, power grids, GPS networks, radio communications. The objective is not simply to understand, but to anticipate, to shield societies from what the sun might send. Real-time monitoring, warning thresholds, redundancy in critical infrastructure. These are now part of human planning, yet many questions persist like shadows at the edge of a candlelight. Can the timing of the next solar maximum be predicted with precision? Models differ in amplitude and phase estimations. Some suggest cycle 25 may be unusually strong. Others see more modest growth. Observations of rising sunspot complexity and flare energy supply hints. But predictions remain probabilistic, not certain. Another concern: is Earth overdue for a Carrington-scale event? A solar storm so powerful that its geomagnetic effects could cripple modern infrastructure. The Carrington event of 1859 exposed telegraph wires to sparks, auroras visible near the equator. Today's technology, power grids, electric satellites, communication backbones, rests on thin margins. What would a similar event mean now? Scientists gauge probabilities, construct worst-case scenarios, devise protective measures. Longer still is the deeper question: is there a cycle centuries or millennia in length that guides the sun beyond the familiar 11-year rhythm? Proxy data, ice cores, tree rings, cosmogenic isotopes hint at longer modulations. Grand minima, epochs during which the sun grows quieter for extended periods. Patterns in auroral records and climate anomalies suggest that solar behavior might shift unpredictably over longer timescales. Are those shifts looming? These tools and missions do not give final answers, but they shrink the unknown. They map change, reveal complexity, register movement in what once seemed constant. The sun is being touched, measured, heard in its deepest whispers. Humanity's instruments now hover on the verge of revelation, and the questions they pursue are urgent, existential. When the sun next peaks, what will it unleash? How close are we, not just to witnessing solar fury, but to living through it? Is the sun merely a star in familiar rhythm, or becoming something stranger, something with new power, new behavior? The sun has been called many things: a god, a furnace, a lamp, a star among countless stars. Yet to Earth it is singular, unmatched. It is the first thing every living creature has ever seen, even if only as warmth on skin or energy stored in leaf and grain. It is the architect of days, the silent clock by which seasons march. Its light falls without judgment, giving life equally to the predator and the prey, the flower and the stone. And yet, it is no passive guardian. The same fire that warms the oceans can ignite storms that reach across space to strike the planet. It is both life-giver and destroyer, calm and cataclysm. The illusion of constancy, which human eyes held for so many millennia, has been replaced with a more complex truth. The sun is alive in its own way, breathing through its cycles, pulsing through its magnetic heart, shifting in brightness and temper across eons. Every sunrise, then, is not merely a rotation of a planet, but a momentary alignment with a cosmic engine whose temperament we barely comprehend. Each dawn is a gift, fragile and impermanent. Humanity stands under this light as both witness and dependent, shaping its civilization under the knowledge that one day, that same star will grow too bright, too large, too violent for life as we know it to endure. The sun will not last forever. In 5 billion years, it will exhaust its hydrogen, swell into a red giant, strip Earth of its oceans, its atmosphere, its last traces of habitability. Long before that final act, its gradual brightening will test the resilience of life, perhaps driving humanity to seek other worlds or to remake itself entirely. But this is the cosmic covenant, that our story is written in its light. The rise and fall of civilizations, the beat of hearts, the germination of every seed. Each of these moments is measured by the rhythm of a star that blazes above. And as the sun changes, so must we. We must learn to understand its moods, anticipate its storms, harden our fragile world against its fury, and yet remain humble before its power. It is a reminder that we are not separate from the cosmos but children of it. The sun is our origin and our fate, a celestial clock marking out the span of possibility. Its ticking is not measured in seconds, but in flares and cycles, in magnetic flips and millennia. And so the chapter closes where it began, with the light that shaped us, that still shapes us, that will outlast everything we build. As the sun continues its quiet transformations, it asks no permission. It simply burns, as it always has, as it always will, until its last breath. In that light, humanity is small but not insignificant. For in learning the language of the sun, in daring to watch it, to measure it, to understand it, we are not merely surviving. We are becoming something new, a species aware of its star, aware of its cosmic clock, and aware that its destiny is to endure far enough into time to see what comes next.